Hi there. Welcome to Lecture 9 of Fox. We're talking about sums and asymptotics. Now, sums are relevant in computer science because algorithm analysis usually involves analyzing sums. And then we're only interested typically in how these algorithms behave for very, very large inputs. And that makes asymptotic analysis very relevant to computer science. Okay. Now, before we start, let's talk about where we were from last lecture. Okay. We have this entourage of proof techniques now, all various proof techniques, but in particular induction. And in particular, we talked about a flavor of induction called structural induction, which applies to recursively defined, functions, structures, sets, the kinds of things that the kind of techniques that we use to define data structures very often in computer science. Okay? And so to prove things about these sets, these recursively defined objects, we use structural induction, and we showed many examples, matched parentheses, formal definition of the natural numbers, palindromes, arithmetic expressions, rooted binary trees. So you see all of these things, they pop up in computer science, they're all recursively defined, sets or structures, and we use induction to prove things about them. And when you use recursion in any way whatsoever, it's very dangerous. So it's especially important to be careful and prove that, whatever you have defined recursively has the properties you intended it to have. Okay, now, what's in store for today? We are going to talk about sums and asymptotics. So we'll spend a fair amount of time on, how do you compute sums, and we'll tackle a few fairly complicated sums and see if we can get closed form, solutions for those sums. And that's typically what it means to compute a sum. But then, why are sums important? Because, when we analyze algorithms do sequential steps, and then we add up the time it takes to do each of those steps, and now we've got the running time of the algorithm. So we compute the sum, but sometimes getting those sums may either be hard or, the functional form of those sums is very ugly. And so we would like rough ways to compare algorithms, i.e. their running times, i.e. the sums that involve their running times, or the functions that involve their running time, for inputs that are relevant to computer science, i.e. for very, 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 very large inputs. And that means that we need to study the asymptotic behavior of sums and in general asymptotic behavior of functions. So we will introduce very convenient notation, and you might have seen this notation flying around computer science called big-Theta, big O, big omega. Sometimes someone will say, well, this algorithm's running time is big O of n, which means it's linear. Okay, all these big fancy words. Well, we'll see what all these things mean today. At the end, I'm going to give you a little gem, okay, which is, we can use calculus to get a very efficient and relatively easy in general method for approximating sums, called the integration method. So, okay, that's going to require some calculus, and so we may even use calculus in this lecture. So stay tuned. Look at the amount of excitement we have in store. Okay, let's start with some motivation, and consider this list of numbers: 1, -1, -1, and so forth. Okay, and I'm highlighting a substring of this list, okay, of 3 numbers, and the sum is 2 + 3 + 4, which is 9. So we could ask, what is the maximum possible substring sum? Okay. Now in this case, you can find a substring of sum 12, and that turns out to be the maximum. If you start at this 2 here, and you go all the way up to this 3 here, you get a substring of sum 12. Okay. Now we might ask, okay, what's the general formulation of this problem? So in its general formulation, we would say that you have a list A1 up to AN, so n numbers, and you can think of n as measuring the size of the input. Okay. So the number of elements in my input. And now we could ask, what's the maximum substring sum for a general input list? Now you can write a program that reads in this list and, outputs the sum. Okay, and a simple algorithm for this is to, start a counter at the beginning of your substring, start a second counter for the end of your substring, and a third counter that goes from the beginning to the end and adds them up. And then, you move the first and second counter and try all possible, values, and then you have this inner loop that, sums given the beginning and end, so you'll end up with 3 nested for loops. Okay, and if you write this program and you analyze it, now forget about how you analyze it, you'll learn how to do that later. Okay, you'll find that this program with 3 for loops will have a running time given by this beast of an expression. Okay, and we call this, a nested, sum. Okay, actually there are 3 nestings, 1, 2, 3. Okay, and you might wonder, what is this summation notation? This sigma, this strange-looking character sigma, the sum from 1 to n. Okay, so Pop Quiz 9.1 in the text is going to give you a lot of practice with that. So look carefully at Pop Quiz 9.1. Do it Okay, we'll touch on it, what exactly that means, when we start discussing how to compute sums. Okay, but the point is that the running time of the algorithm with 3 for loops is expressed as a sum, in particular as a nested sum. Okay, now you can do better. You can do 2 for loops. Okay, you can find an algorithm that doesn't need 3 nested for loops, and actually there's even a recursive algorithm for this problem. And here's a challenge for you. It's possible to compute the maximum substring sum with just 1 for loop. Okay, and the running time for this algorithm with just 1 for loop is given by this much simpler looking expression. Okay, so you might be wondering, wow, have I got to take all this in? How do I do this? How do I do? No. You don't have to pass these sums. The important point here is twofold. The first is that when we program algorithms for even such simple problems, when you analyze the runtime is expressed as a sum or a nested sum. Okay? Or in the case of a recursive function, the runtime, and we saw recursive functions before, the running time for a recursive function will typically be satisfying some kind of recurrence relation. So, the running time or the running time at n is, okay, there's a base case, but basically the running time at n is, twice the running time for n over 2 plus something. Okay, so that's a recursion. The running time satisfies a recursion. Okay. So, recurrences, recursions, sums, they're popping up in the analysis of algorithms. Okay. And, what we see here is that you and your 3 other friends come up with 4 algorithms and they have different running times. And then the question becomes, which one is best? Okay. So here, why don't we just evaluate the runtime? Okay, so the running time for the first algorithm is is 2 plus a sum. So this sigma is a sum of something which involves a sum of something which involves a sum. So it's this complicated sum. Well, actually we can program a function to compute this sum, and you can go ahead and do it. Compute this sum for different values of n. And at the end of this lecture, you'll know how to compute sums. So you can go and compute this sum. Again, I've done it for you here. The running time, according to this sum, the running time for algorithm 1 is 11 when the input size is 1. Wow! Okay, the list has just 1 input. The running time is 11 because it has to initialize 3 for loops and all kinds of things are going on. Okay, when n equals 2, 29, 58, 100, and so forth. Okay. You might wonder why is this highlighted in red, 29, and so on, because we can do the same thing for the second algorithm. So we can compute its running time, t2 of n, okay, and we can ask is t2 better than t1, and so that's what I've plotted here, okay, and t2 of n, again, the running time when n equals 1 is 11, okay, similar to t1, but then it got better, 26 instead of 29, 47, 74, and so forth, and you see that t2 is always better than t1, no matter what n is, okay, except for the input of size 1, where they're equal. Okay, let's ignore that, okay, but it's never worse, t2 is never worse. So we could ask, what about, okay, so we would never choose t1 over t2, but what about t3, that fancy-looking recursive algorithm? So we can program that recursion and compute t3 of n, okay, and now things have gotten complicated. Unlike the situation with T2 and T1, where T2 is clearly better, T3 is much better. Okay, much better when n equals 1. Its running time is just 3. Okay, but then it got much worse. Okay, running time 27 for n equals 2, and then 57. Okay, a little bit worse than T2. Then 87, 123, 159, 195. Now they're starting to look comparable. And then, at n equals 8, look what happened. T3 became better than T2, and then it's got even better, and then even better, and so it looks like something very strange is going on. Okay, the third algorithm starts out well, okay, got worse, and then got better than T2. So which one is better? Okay, and it seems like determining whether you're going to use algorithm 2 or algorithm 3 in terms of runtime depends on what's the input n. Okay, but then what about T4? Okay, so T4 is also interesting. T4 is much worse than all the algorithms when n equals 1. Much worse than all the algorithms when n equals 1. But then look, when n equals 2, it's gotten better than all the algorithms. So it went from being the worst to being the best all of a sudden. And then it turns out that it never loses to any of the algorithms after that. Okay. Now, when you look at this, you see that comparing the running times of algorithms, or comparing algorithms in general, is a fairly hairy business. How do we do it? I mean, here, simple problem, 4 basic algorithms, And there's no clear winner, okay, unless you specify n. If you were to tell me that n is 1, then I'm going to use T3. If you were to tell me that n is, 9, I'm going to use T4. Okay. So, two things come out of this. Okay. The first, we need a way to sort of get simplified expressions, for the running times that involve sums and recurrences. Okay. We need simplified expressions for T1, T2, T3, and T4. I mean, what we see here is just, a big mess. Okay. And the second thing that should hopefully come out is that, we need a way to compare runtime functions. Okay. We need to compare running time functions like T1, T2, T3, T4 in order to determine which algorithm is the best. And the way we compare these running times should capture the essence of the algorithm, perhaps not a specific input n. Okay. And so, first, let's deal with the first issue of, how can we compute sums? And then we'll talk about, how can we compare the running times once we have computed, simplified expressions for the sums. And in this discussion of comparing, we have to capture the essence of an algorithm, and we'll simplify even further. Okay. And so, let's go to the board.